Let's take the next problem, which is 11-25 of our book. It says an automobile radiator may be viewed as a cross-flow heat exchanger with both fluids unmixed. So as we know, a radiator has got two fluids. One is the water and the other one is the air. So it says that water, which has a mass flow rate of 0.05 kilograms per second, so that would be the mass flow rate of water, enters the radiator at 400 Kelvin and leaves at 330 Kelvin. It enters at 400 Kelvin and it leaves at 330 Kelvin. And the water is cooled by air. So water would be cooled by air. So of course the water would be the hot fluid. So its temperature comes down from 400 to 300. So that would be THI, and this would be 330 would be TH outside, TH at exit. So this is the solution that we are taking a look at. So it is 11-25. So water is the hot fluid having a mass flow rate of 0.05 kilograms per second, and it comes in at a temperature of 400 Kelvin and it leaves at a temperature of 330 Kelvin. Now the water is cooled by air, so air would be the one which is getting the energy. So it would be the cold fluid. Air would be the cold fluid, and since it is getting energy by water, its temperature will start going up. So air enters. So let's first write air as the cold fluid. So air is the cold fluid. You need to have those two columns for your own reference. So the water is cooled by air. So air is the cold fluid which enters at 0.75 kilograms per second and 300 Kelvin. So air comes in at 300 Kelvin. So that would be TCI. So TCI would be 300 Kelvin. And the mass flow rate of air means mass flow rate of cold fluid is 0.75 kilograms per second. Now if the overall heat transfer coefficient is 200 watts per meter square Kelvin, so we are given the value of U. What is the required heat transfer area? So we need to find out the area if the overall heat transfer coefficient is 200 watts per meter square Kelvin. This 200 watt is not limited to this column only, rather it should have been written between the two columns. So we need to find out the area of the heat exchanger. Over here we would not be able to use LMTD method at this point in time. The reason is that we do not know all the four temperatures, rather we only know three. We know both the temperatures of the hot inlet and hot outlet, but we only know the cold inlet temperature and not the cold outlet temperature. So at this point in time, we would not be able to calculate LMTD. However, we can always calculate Q with the help of MC delta T applied over on the hot fluid side. So it would be mass flow rate times Cp of hot fluid times THin minus TH out, as discussed in the previous problem of 11-22. So over here the average temperature would be the average of 400 and 330, which would be 365, and then we will go to that property table of water as I was showing you earlier, and at a mean temperature of 365, at a mean temperature of so this is the table for the properties of water. So at mean temperature of you can see over here 365 Kelvin. So at 365, this would be the row of our interest. The value of Cp is given to us as 4.209. So that would be 4.209 kilojoules per kg per Kelvin. So we get Q as 14731.5 watts. Now we will now apply the same expression over on the cold side, on the cold fluid, which is air. But the thing is that we do not know the temperature of the cold air. So we will be finding out the temperature of the exit temperature of air, cold fluid from here. So, but the problem is that we need to find out the specific heat of air at a certain average temperature. So we are given the inlet temperature as 300, but we do not know the exit temperature. So what you can do is that you can take a look at the average at various values of Cp of air. It is water. So let me see where we have got the air at. So that is this table A4 has got the properties of air listed, right? So if you take a look at the values of Cp, one temperature is 300 Kelvin, right? So at around 300 Kelvin, it is 1.007, and it is hot fluid, so its temperature will eventually go up. So we should be going downwards, and 1.009 and 1.004. So if we assume it for the time being as 1.009 and use the same expression of Q, 14731.5, and write its Cp as 1.009, we will get the outlet temperature as 320. This is for the sake of finding out a good guess of Tc naught, and this guess is only being made to find out the average temperature so that we can look for the value of Cp from the table. That is the only reason. So we will get the value of Cp as 1.008 then, and probably you would have understood it that we put that Q is equal to mc delta T to find out a good guess of Tc naught. I mean, we need to have this particular value so that we can find out average temperature, so that we can find out the value of Cp. So that is the engineering procedure to find a reasonable value of Tc naught. And once we find out the value of Cp, we will put it over here, and then we would be able to find out the actual value of Tc naught as 319.486, right? So Tc naught will come out to be 319.486. Now we know all the four temperatures. If we decide to use the epsilon NTU method, so this is how we will proceed. See, this is the case where we have see, let's look at the type of the heat exchanger. It is a cross flow heat exchanger with both fluids unmixed. So if we go over here and then we go to this list, these charts. So the first one is for effectiveness of, rather this is the first one, this is for parallel flow, and then this is for counter flow, This is for one shell and multiple of 2 tube passes. This is for 2 shell passes and multiple of 4 tube passes. And then this is the one for heat exchanger with both fluids unmixed. Cross flow heat exchanger with both fluids unmixed. So if you look over here, so we need to find out epsilon and Cmin over Cmax so that we can find out NTU, and once we find out NTU, we will equate it to UA over Cmin, and we would be able to calculate the area. This is the procedure that will be adopted if we decide to go with Effectiveness-NTU method. Now we need to calculate two things, epsilon and Cmin over Cmax. Now epsilon is let's calculate C first, because epsilon would require the calculation of Q as well. So C is Cmin over Cmax. Now we need to multiply this mass flow rate with Cp of H. So if you multiply 0.05 with 4.209 exponent 3, we get a value of 210.45. So CH is 210.45. Right? And if you multiply this cold fluid mass flow rate with its Cp, means if you multiply 0.75 with 1.008 exponent 3, we get a value of 756. So out of 756 and 210 is the Cmin and Cmax is 756. So 210 will go into the numerator and 756 will appear in the denominator, and this ratio will be 0.278. So we have found out the value of Cmin over Cmax. We have found out the value of Cmin over Cmax. The last thing that we need to find out is the value of effectiveness. Effectiveness, as discussed in the theoretical part, was the ratio of the actual heat transfer to the maximum heat transfer rate, Q over Qmax, and Qmax was evaluated using Cmin times this delta T, because this delta T would be the maximum. This is the delta T of the maximum temperature out of the 4 and minimum temperature out of the 4. So Cmin is 210.45, and then THI is 400 and TCI is 300. So we will get maximum Q as 210.2045 because it is 210.45 being multiplied by 100. So this would be 21045 watts. So Q, which was calculated as 14731 divided by 21045, would give us 0.7. So effectiveness is 0.7. Now if we go over here on this chart, and if we intersect the two values, effectiveness is 0.7, means this line is 0.7, between 0.6 and 0.8 would be 0.7, and then C is 0.27. So we have got this line of 0.25, so it would be just a little bit above 0.25. So if we follow 0.25 up till this 0.75, and if we go just above that, and if we come over here, it is just less than 1.5. You may take it as 1.45 or 1.5. Right, so NTU would come out to be 1.45 or 1.5. I have taken it as 1.5. So NTU is, since it is equal to UA over Cmin, will give us the area as 1.578 square meter. So this would be the area of the heat exchanger. And as I told you earlier that there are two methods, the LMTD method or the Effectiveness-NTU method. So if it is a choice, then you may use either of the methods. However, if you go with LMTD method, so then you would require U times A times LMTD and correction factor. So after finding out the LMTD, you need to calculate correction factor as well, and then you need to calculate U as well. And calculation of U would be 1 over Hi plus 1 over H naught. And in this particular problem, we are not given any of the values of the convection coefficients. So the convection coefficient calculation is very extensive, and you would have seen that in 1122 we had spent a good amount of time for the calculation of Hi. We first had calculated Reynolds number, and then we selected a value, an expression of Nusselt number. We calculated the value of Nusselt number and equated to Hd over K. So if you go to LMTD, that may be quite extensive and quite lengthy. So over here, since it was a choice, so I showed you that that the use of effectiveness NTU would be a better choice, because it won't take that long to calculate the required area of the heat exchanger. So that is all about 1125.
Next problem, which is 11-32, says that a single pass cross flow heat exchanger. So it is a cross flow heat exchanger, uses hot exhaust gases which are mixed. So to heat water which is unmixed. So the water is unmixed, so that would be flowing through the tubes, and hot exhaust gases would be outside the tubes, and they are mixed with respect to direction as discussed earlier. To heat the water from 30 to 80 degrees Celsius at a rate of 3 kilograms per second. So water would be the cold fluid and exhaust gases would be the hot fluid. So T cold in is 30 and T cold out is 80. If you take a look over here, it is 1132 cross fluid exchanger. So T cold in is 30 and T cold out is 80, where it is the cold water which is unmixed and the hot gases are mixed. The exhaust gases having thermophysical properties similar to air, having similar properties, having properties similar to air. So we may use the properties of air uh, in place of the properties of exhaust gases, which you would have realized in other courses as well. Because sometimes we take gamma for air as 1.4 and we take the gamma of exhaust gases as 1.33. So there are several things that are close to, several properties which are close to each other. The exhaust gases having thermophysical properties similar to air enter and exit the exchanger at 225 degrees and 100 degrees respectively. So this would be pH in and this would be pH out. So we are given the values of pH in as 225 and pH out as 100. If the overall heat transfer coefficient is 200 watts per meter square Kelvin, we have to estimate the required surface area. So this problem shouldn't be difficult at all. We will find the average temperature. We are given all four temperatures. So and we are given U as well. So we can either use the LMTD approach or the Effectiveness-NTU method. If you use LMTD approach, um, we can find out Q using MC delta T of the cold side, and then we can find out, we can write Q is equal to MC delta T for the hot side, and we will then find out mass flow rate of the hot fluid, and then we can use Q is equal to LMTD for a times correction factor. So U has been provided, area is the unknown quantity, logging temperature difference can be found out since all the four temperatures have been provided, and since all the four temperatures have been provided, we would be able to find out the correction factor from the chart. So this is how we would be able to proceed. Now If we want to proceed using the other method of effectiveness-NTU method, and again we will be finding out area as we had found out in the previous problem using NTU is equal to UA over Cmin. So first of all, we will do the same thing. I mean, the first two steps will be the same, whether we use an MPT approach or whether we use effectiveness NTU approach. So we will be using Q is equal to mc delta T for the cold fluid because we know all the parameters of the cold fluid. The average temperature will be 55 degrees Celsius, means 628 Kelvin for water, and we will then find out the properties of water at that particular temperature, average temperature, which is 328 Kelvin. So at 328 Kelvin, so we are given properties at 325 and 330. At 325, Cp is 4.182 and it is 4.184. So it might be 4.183. 4.183 kilojoules per kg per Kelvin. So we will put that value of Cp over here along with the mass flow rate, which is given to us as 3 kilograms per second times delta T, and we get Q as 627,450 watts. Now, if we then equate or write this Q in terms of the hot fluid, we will write it in this form, where the unknown would be the mass flow rate of the hot fluid. So we will be able to calculate the mass flow rate of hot fluid as 4.9 kilograms per second. And in here, we would require the value of Cp of air. Of hot gases means similar to air, where the average temperature would be 225 plus 100 means 325 by 2 means 162.5, which would be 435.5 Kelvin. So if we go to the properties table and we find air, it is there in table A-4. These are the properties of air. And the average temperature is 435.5 Kelvin. So at 400, we are given properties at 400 and 450. At 400, the Cp is 1.014, and at 450, it is 1.021. So we need to interpolate for 35.5 difference. So we will eventually get Cp as 1.0189 kilojoules per kg per Kelvin, which will be put over here. So eventually we will be able to get the mass flow rate of the hot fluid to these hot exhaust gases as 4.9 kilograms per second. Then, if we go further to now, we need to find out NTU and Cmin. So the product of 3 and 4.183 exponent 3 uh, would be 12549, and the product of 4.926 and 1.0189 exponent 3 would be 5019.6. So out of the two, this 5000 is the lesser one. This would be called as Cmin, and this 12,000 is the greater one. Therefore, it would be called as Cmax. Therefore, Cmin over Cmax means 5019 over 12549 will give us a value of 0.4. So out of the expressions, out of the values in this expression, we also have found out Cmin. So the last thing is to find out NTU. If we go and find out NTU, NTU can be found out using those expressions or the table. If we refer to if we refer to those charts, this is for parallel flow, this is for counter flow, this is for one shell and multiple of two fluid passes, two shell and multiple of four fluid passes, and this is for cross flow. And this is uh, for both fluids mix, and this is for one fluid mix and one unmixed. So if we use this expression, um, if we use this particular chart, we will be able to in order to use that chart, we need to have the value of epsilon as well. Because over here we can see that along with Cmin over Cmax, we need to have the value of epsilon to find out NTU or NTU to find out epsilon. Since we are trying to find out NTU, so we should be able to calculate epsilon. So epsilon is Q over Qmax, where Q is 627,450 watts. And then if you want to find out the other thing which is Qmax. Now in order to find out Qmax, we need to use this expression of Cmin times maximum delta T. And as discussed before, the maximum delta T would happen the when we take the temperature difference of the maximum and the minimum value. Uh, so therefore, um, if we work the things out, so we would be able to calculate this Qmax as 9788 kg because Cmin is 5019.6 and Phi is given to us as 225 and Ci is given to us as 30. So if you put the values, we will get this value of Qmax, and the ratio of Q to Qmax will be 0.641. Now, if we from that chart that I was showing, you would be able to get the value of NTU as 1.4. Or NTU can also be found out using that expression, but if we have got the chart that are always easier to use as compared to the expressions. So therefore we get NTU as 1.4, and putting NTU in equation A, we would be able to get the area as 33 square meter.